Start from this topic. For today, I don't think we'll go in much details about the medical part. We will do a recap about digital images. That's the part I was asking before about what do you know about signal processing. Now, what is a digital image? A digital image is basically an array of numbers. It's not really that nice on this screen. Okay. I hope it will be clear enough. Because I have, in this part, I have lots of examples about images and human perception, but if the contrast that we see on screen is like this, probably it's not that good. Well, whatever, let's try anyway. So a digital image is an array of numbers. So if you start zooming in this test image, you can start to see that you have individual squares. These squares are called pixels, or sometimes in medical images, voxel if you have, because pixel is an abbreviation of picture element. If you have a 3D image, these are called voxels, which means volumetric elements. To me, you can use them interchangeably. If you, let's say, zoom in again, you find an actual matrix of numbers, which is something like that, 0, 0, 0, 10, and so on. They are discrete numbers. So we have said we have an array. The next question is, which is the dimensionality of the array? And actually, it can be a lot of things in medical images. When you have images, you have pictures, let's say. You have this a 2D planar image, which has 2 dimensions, which are x and y. And actually, when it's a picture done from your camera, it's actually n number of pixels along the axis x, number of pixels along the axis y, and 3, which is the number of channels, which is red, green, and blue. However, you can also have a 3D volume. It's quite common in vivo medical images. You have a stack of planes, and these stacks of planes, you have 3 axes, x, y, and z. However, you can also have other kinds of 3D arrays. We have already seen 2 types. The third one is a time series, which is actually what you get if you load in Python a movie shot from your phone. So you have the number of pixels on the 2 axes, and along the time dimension, the number of frames, which can be lots. If you have a movie with 25 frames per second for 2 hours, that's going to be like up to 1 million. And if you start thinking about in this way, medical images can be of really lots of dimensionalities. They can go up to 7 dimensions, because you can have a 3D volume over time with multiple parameters per pixels, so you can have really lots of dimension, because you can also save tensors of orientations, how something is oriented in 3 dimensions along each parameter. There are, in MR acquisitions, there are possibilities to do maps of blood flow in the heart. And so for each pixel of the heart, you have the direction and the speed of the blood in that pixel. So you can see how easily you get to 6 dimensions. If you add how this changes over time, how the speed of the blood changes during the cardiac beat, you get to 7 dimensions. Now, this is a pretty important concept, which it's easy to overlook. We have said we have an array, but which kind of numbers are inside this array? There are multiple possible answers for that. There are some in pictures, like the ones that you have on your phone. The numbers are bounded. So generally, you have you have 8 bits of resolution per color. We'll come back to that when we'll talk about screens. And therefore, you have numbers that are bounded. And they go generally in a range that can be from 0 to 1 or from 0 to 255. This is irrelevant. This depends only on your data format. You can also have a completely arbitrary unbounded scale, which means a meaningless number. In many MR images, you have this kind of data. So like you take a look at one pixel and it says 15,000 watt, whatever, it's irrelevant. And which means that then you need to find a way to transform this into something that makes sense. And generally you do that thinking about the human vision. The last possibility is that you have a physical scale. Like in CT images, the images have a unit of measure which is of density. It's its own special unit, but you can think it of density like in grams per cubic centimeters. So that if you get the number 0 in CT, as opposed to 1, this means density of water. If you get 100, it means density of muscle. If you get -10, it means density of fat. If you get 1,000, it means density of bones. So these are numbers that have an intrinsic meaning. Therefore, this needs to be kept into account. Now, how do we save these numbers? In multiple numerical formats. The first version is unsigned integer, which go between 0 and 255. And this is the most common format for pictures. This is what you get if you unpack the image you have on your phones. And this can be used in medicine. It's a format that can be pretty typical of histology, which is you look at something with a microscope, you put a camera on top of the microscope, you take a picture, and that's what you get. In dermatology, you have these devices that in the end are cameras that you put on top of on the skin when there is a suspect lesion. It takes a picture, and that's what you get. Nowadays, sometimes they use more resolution. Like nowadays, last 5 years at most. But often it's not even needed. Now, this used to be the most common format ever for storing the data in medical imaging, because this divides all the intensity range that you need to represent in 65,000 steps. Generally, everything that you can measure that makes sense, these are more than enough. Like if you have a CT, however, that has the numbers that go from -1,000 to +1,000, you can still use this. Because you save your array with 16 bits, and then you save one parameter, which is a slope and translation parameter. It is two numbers that do scaling, and so you can translate all this dynamic range into whatever interval, single or double precision interval that you might need. Nowadays, sometimes for very high resolution formats like MR, sometimes they save also things in single precision, which takes 32 bits per pixel. Of course, these use double the space on disk. This used to be a very huge concern. Nowadays, not that much. And however, this is the best format for pre-processing data, for processing data, while this generally is the best one for storing data. This one, for all modalities, excluding the ones that are pictures, it has too little resolution. Now, be careful about the format that you're using in general, because if you are working with 8-bit precision, and you start doing calculation, you soon lose a lot of data. I have also a very simple example. We have two arrays of 4 by 4. You can think of that as images, even if they are just 4 pixels. What happens if you do a subtraction between this and that? Like if you do 0 minus 2, what happens? Well, it's not defined, because if you're working with positive numbers, you don't have minus 2. So in MATLAB, it truncates to 0. And in Python, it depends on your Python version, actually. You get 254, which is maximum minus 2. So this is not something you want. If you have to do a division, this is what you get. If you do 200 divided 70, it gives you 3. If you do 86 divided by 0, you get 255. And I did this in MATLAB because actually in Python, it forces the results in float. Then if you can do float and then round it again, but it's a different concept. Now be careful, even if you're working with 16-bit that has lots of dynamic range, if you do an operation like this, you divide by 300 and then multiply by 300, you basically end up cropping lots of significant digits. And this is, well, this is not really something you want. And of course, one thing that you always need to remember, precision loss is not reversible. When you've lost some data, if you delete them, you lose them. Okay. Any question about this? I'd say we can start a new topic and then take a break after 20 minutes or so. Now, this is a very important, I will talk about this in general, not related to medical images. This is how the human eye, well, it's not really the human eye, the complex human eye plus brain, because the brain plays a really huge part in that, how this works. And we need to remember this because even if you develop the most advanced artificial intelligence system, it probably needs to take a look at the same things that a human will take a look at. Oops, sorry. So the human eye is, the eye itself is an optical system. We can see that as an optical system. We have a lens, which is made by the cornea plus the crystalline, plus a detector, which is the retina. There are two detectors within the retina, one dedicated to day vision in high luminosity and one dedicated to night vision. The night vision has much less resolution, and actually the eye keeps on moving, and only the very center of the eye is able to have a very high resolution. Most of the eye doesn't see that well, but the eye keeps scanning, actually. It's interesting to note that the eye is able to see over 7 orders of magnitude of brightness. You need some minutes of adaptation, but if you are on the top of the mountain, on a daylight, on top of snow which reflects a lot of light, on top of a glacier, you are able to see. This is really an immense amount of light. You shouldn't do that because it's really too much and you should be wearing sunglasses. And if you are in the night, in the middle of a field, even with a court with no trees on the top of your head, if you stay there for 10 minutes, you still see, if you have a clear sky and there are some stars, even with no moon, you see enough to walk and to see what's on the ground. That's an incredible amount of different levels of light you can look at. However, the eye is so in some way the eye is sensitive over a logarithmic scale of brightness. However, it behaves linearly over some small linear range of luminosity near the mean ambient luminosity, which is the adaptation that I was talking about before. And around 2 orders of magnitude of luminosity, you can see your eye behaves linearly. Like if you are driving and you go inside a tunnel with no lights on the top, you don't see anything, even if your eye will be able to do that. You will need to spend some minutes, and that the opposite when you're coming out. Now, what does your eye see? So if we take a look at this picture, we can see really, this was a picture taken on a cloudy day. You can see very little things. If you enhance it, we prefer this a lot. Now, the first things that your eye looks at is contrast. What you see is not light. It's contrast. It's not light. Of course, it's not darkness, because darkness is the absence of light, so you don't see the darkness. You see the difference in light and colors somehow. So the difference in either luminosity or color between two objects is what you perceive, not the absolute values. And your eye focuses a great deal on contrast. This is, I guess, one of the most famous optical illusions. There are, if you look at the Internet of Optical Illusion, it's full of them, especially because they are extremely useful in understanding how how the human vision works, which is the complex of eye plus brain. And also the brain, neuroscience tells us that there are multiple layers of step of processing. There is the visual cortex, which does a subconscious immediate processing, and then there is a much more complicated and longer object detection involved. And finding objects, cases where your brain fails, tell us how our brain is working. So they're not just funny situations. They're quite useful. So this is a typical optical illusion. The square A and the square B have exactly the same level of brightness, but given that our brain focuses so much on contrast, we perceive them as having two different kind of luminosity. Is this clear? Okay. Now, next thing, if you take a look at this image, which you might think of as a pencil sketch, you can, I hope, you can recognize what it is. It's a kind of medieval mansion, and you might even recognize that we have some woods there. Here we have a reflection, so we understand that there is a water, probably a lake, that does a reflection. But actually, this is not a pencil sketch. This is just the mathematical gradient of the intensity of this image. These are what we can call the edges of the image. And edges are actually the most powerful feature that our brain focuses on. Our brain really goes looking for discontinuities in an image. This is one of the most important features we focus on. So generally, when we want to build the denoising method, we want to preserve images as much as we can. When we want to sometimes maybe medical images, actually edges are not that prominent, because sometimes maybe what's relevant is the average intensity over a large area, which is something that appears as a kind of a small gradient, a kind of a blob. And this is something that our brain might instead miss. So that's something that we really need to keep in mind. Now, continuing, I hope this screen shows well enough. Just to give you an example, this is a picture of a landscape. If I apply a very small level of blurring, which if you take a look at the the difference between the two arrays is actually really, really minimal. I don't know if you perceive it from the classroom, but you should like this one a lot better than this one. I don't know if you get this from there. Okay. That was just an example. The next thing our brain really focuses is patterns. So if I ask you what this is, of course, you don't have any clue. If I do, this is really a cartoon sketch. It's not even a picture. You can always say this is a raw piece of wood. Even if it's just, this is a really stupid drawing of poor quality. And this shows you the how our brain works, because most object detection happens thanks to the recognition of patterns. This means that the prior knowledge that we have, the experience of reality we have, enters massively in vision, in object recognition. The next thing that's not really an issue in medical imaging, but just to be complete, is illumination. Now, this is basically the same thing. If you look at the first image, that's the drawing of a circle. If we just add a bit of light here and a bit of shade around here, our brain says, OK, this is a 3D image. Now, there's no 3D. This is not a stereotactic vision. We are looking with just one eye. Yet, our brain says, OK, this is a sphere. This is not a circle. Again, this is all based on prior knowledge. This is just from everyday experience. Our brain is trained like it was a neural network on recognizing that if we have shade, then it probably is a 3D object. Now, let's talk very quickly about spatial resolution. Probably you have some experience from your vacation pictures and things like that. You probably, if I ask you how many pictures you get in an image, you're going to say, I don't know, like 1,000 times 2,000 or things like that. This is all, and if I talk about a 128 times 128 image, you say, OK, this is not even displayable, so given how small it is. Now, actually, you probably know the sampling theory, the sampling theorem, under the name of Fourier or Nyquist, Shannon, or even sampling theorem name itself. It says, not really in the mathematical, this is a less strict version, not the mathematical one. It says that you can reconstruct perfectly any detail of dimension around 2 pixels. Therefore, small images can really still contain a lot of useful detail. You will do some exercises about that in the Python notebooks. And this means also that huge images generally do not contain a lot of details. Up to 5 years ago, in MR, it was, which is the most high-resolution medical imaging modality there is, you did not get images bigger than 512 times 512. But also, you could get much smaller image. In nuclear medicine, you often work with 128 times 128. And this is still enough. Also, you need to do a distinction between the spatial resolution described by the sampling theorem and what happens with image compression. Image compression is not something that is used in medical imaging because at least the lossy image compression, the JPEG one, because it makes you lose details, and that's not something you want. However, this is needed to make files of huge images smaller by removing the details that we do not need. So if you zoom in on an image of 4,000 times 2,000, probably you don't see a lot of that. So this is something that you need to keep in mind, that in medical images, if you have something as small as a stamp that is 256 times 256, every single pixel in that is meaningful, while if you have a 2,000 times 4,000, probably it's not. Okay, so. Facciamo ancora un quarto d'ora e poi facciamo una tirata unica? Va bene? O facciamo una pausa adesso? Come? Vabbè, facciamo la parte sul rumore, poi ci prendiamo un quarto d'ora di pausa. Boh. Now, in images, when we talk about images, of course, we need to talk about noise. And noise in medical images, at least in some modalities, can be really huge. The question is, how do we define noise? What happens when you talk with physicists, mathematicians, and I guess statisticians, so people with experience in data science and no experience in imaging? They just do, okay, let's say we pick a uniform region, which is hard to define anyway, hard to know a priori where it is, and let's take the standard deviation between all pixels. If we do that, in this image that I just made, we say, okay, the standard deviation is 0.3. The mean value of the signal is 1. The mean value of the background is 0. No, 0.1. And then we can say that the signal to noise ratio is 10 times logarithm in base 10 of the signal to noise ratio, and this is 4.7 dB. If we do this, then I can come with a counterexample. This has exactly the same signal to noise ratio, but would you say that this is the same noise? I guess that we all agree that it's a completely different thing. Now, this is another example. These two images have the same signal to noise ratio. Would you say that the signal, which, by the way, if you think about it, I haven't defined the signal, but you are already able to know that the signal for me is this yellow square. Would you say that the signal is equally visible? Probably no. And the question is why. You will need to remember that even more in medical imaging, the concept of noise is actually task dependent. Because here the question is a, let's say, 1 centimeter square recognizable over a noise that has a correlation of, that has lots of blob of 2 millimeters? Say, well, of course. In this case here, the square that we want to know if it's present or not is of the same dimension of the blobs of noise, so they are different to pick apart. Also, there are many kinds of things that we can call noise. This is what I was showing you is low frequency noise that are lots of blobs. Here it's some purely random noise, which is, however, Poisson distributed. In each pixel, the probability depends on the mean intensity of the light that is there. This is typical of how many detectors work. There can also be high frequency noise. There is more noise at higher frequencies than lower frequencies, and this is typical of CT images, and it's especially bad because it hides edges, because edges by definition are high frequencies. And also, we were talking about compression before. If we compress a lot one image using JPEG, we can get this kind of artifacts here, this kind of somehow correlated blobs. These are not random, but we can call this noise because to every effect on the human vision, it's something that hides our targets. So it's something interesting. There is also a task, I was mentioning before that we have a task-specific definition of noise. Here we have a 10 pixel wide square. We have a very huge level of noise. The standard deviation is slightly bigger than the signal itself. The signal-to-noise ratio is therefore negative. But if I filter this image with a Gaussian kernel, we can recover that because we hide all the frequencies. So if my question is there some kind of signal on a scale which is big enough compared to the noise, the answer is yes. And so in this case, if I again define the signal-to-noise ratio, I get a very large one. If I take a much smaller signal, I get the same level of signal-to-noise ratio. And if I do the same kind of filtering, do I still have the signal? Well, that's a hard question because technically I have enough signal. I don't know if it's 5, it's enough, but in this specific noise realization, we have both the signal and the noise can have the same kind of intensity. Now, this is not the topic of the course, but it's just to remember we should not forget human perception. If we want to filter out the noise, which one is optimal? Probably from the signal-to-noise ratio, this one is better because the noise is really zero. But the human eye likes edges a lot, so we probably prefer the second one. So let's take a look at the possible sources of noise. There are lots of detectors from our phone camera to the detectors used in X-ray imaging that are used both in plan or X-rays to CT scans. Count photons. So you have a Poisson process. If you work in a field with lots of photons, like X-ray is in many conditions, you have a Gaussian with a standard deviation, which goes with the number of counts. Some detectors can have some level of background counts. There are other forms of noise, and then there is the noise also introduced by the reconstruction algorithms and by the processing, which can be either introduced or maybe transformed in shape, like go from low frequency to high frequency. If we want to use some fancy statistical terms, these are not things that I will ask you. The simplest noise is so-called static, which means a shift in variance in time and space. You take 4 pictures in sequence, which work exactly like X-ray images. The noise, the level of noise, not the level, the specific intensity due to noise that you get in one picture is completely independent from what you get in the next picture. There is no memory. Ergodic means that each subsample has the same expected mean. So if you take the mean of the noise in one part of the image, in the next part, and so on, it's the same. The noise is independent between pixels. What you get is white noise. White noise works like that, which means that the image you measure is the true image plus a Gaussian with zero mean and a standard deviation sigma. And you can estimate its magnitude from any part of the image. Probably it's not often uncorrelated. This is the purely uncorrelated noise in theory. In most realistic situations, there is some correlation between neighboring pixels. This is from a book that was talking about older detectors more. Nowadays, it's not really like this. The noise can be not static. Some part of the detectors work better than others. And how do we introduce a metric to quantify noise, which is, by the way, the metric used in training a denoising neural network, this one? We have the mean square error. So you take the mean divided by the number of pixels of the difference between your image and a reference gold standard image. We have the signal-to-noise ratio, which is 10 times the logarithm in base 10 of the maximum dynamic range, if your image is not scaled between 0 and 1. Otherwise, this is 1. And the mean square error. This works only when you have gold standards. What are the limits of using this as a metric? Which, by the way, I will tell you in the next 5 minutes all the limits of these metrics, but in the end, even in the artificial intelligence field, you still get back to using these. But at least you should be aware of the limits. So this is your original image. This is the image with some Gaussian noise. So, no, sorry. All these images have almost the same mean square error. But would you really say that these two images are the same as this, which is purely white noise? Also, would you say that this image is noisy? I would say that this is corrupt. And this has some compression artifacts. So there are some huge limits in this. Now, the first two images have modification in the mean intensity. This has higher mean intensity. So it's perceptually identical, but mathematically different. And this has lower contrast. So we like it a bit less, but I will not say that this looks, we should use the term look because we are talking about the perceptual human system like this. It's pretty different. So they came out with an alternative, which is the structural similarity index, which is limited between 0 and 1, and it is the multiplication of 3 perceptual ideas. So it weighs the difference in mean luminosity, in contrast, and in correlation, which takes into account the edges. And this is much more informative for these cases. Now we can see on the same images the differences. In this case, the structural similarity index is 0.92, 0.98 for the first one that looked the same. It's 0.73 in the corrupted one, 0.5 in the one with too much compression, and 0.6 in the one with some blurring. Okay. Now why are we interested in reducing noise in medical imaging? So if we have less statistical noise, we can image in less time. if we have an MR which might be a bit longer, or using less radiation dose. And the less radiation dose is obvious. The imaging time might be very important for some exams, because I don't know, if you take an MR of the liver, you need to take, the liver needs to be static, so you need to tell the patient to stop breathing. So if you can image in less than 30 seconds, that's ideal. If you need 2 minutes, you cannot ask patients to hold their breath for 2 minutes. The limit is around 40 seconds or things like that. Or for, we have some exam in nuclear medicine that take 30 minutes. Of course, if you can shorten imaging time, you can free up more machine time to more patients, but also the exam becomes more tolerable because patients don't like staying on a machine for half an hour. Also, we have some much cooler examples. When you have incomplete data, you get in output some pattern-specific noise, and therefore we can reconstruct images without having all the data that we need. So this is something that we will see in the lectures about advanced denoising, because it's a field that was really, really, I don't know if I want to say revolutionary, but it's extremely important. Okay, so it's 10 to 1. Let's take a break. Let's meet at 2:05. It's okay. Okay, so let's start with the last part where we will, we have some residual slides about how we see images. Now, the images, we've talked about images in abstract until now. We need to see these images somehow. Nowadays, all of medical imaging is based on digital images, so we need to talk about screens. Because up to, let's say, 10 years ago in mammography, they dismissed the last film-based X-ray devices. Now, all of radiology, except maybe some residual application in some very small dedicated context with all devices, it's all digital. We don't have films anymore. Anyone here ever played with films, with film photography? Okay. So film photography had a spectacular spatial resolution. So in mammography, it survived quite a lot, and also in dental imaging, but for the rest, since year 2000, 2010, everything switched to digital. So even planar radiography, they switched to images projected on screens, and screens can show only 225 intensity of lights for each color. Nowadays, some professional radiology ones can show 10 bits of depth. But this means that we don't have that much dynamic range, because the dynamic range of a radiology image can be much more than 255. So we need a very good monitor. Ambient illumination is fundamental. You cannot work with bright daylight around. You cannot work with reflections on the screen. The screens need to be calibrated because its response needs to be linear, which is not trivial. And if you are interested in this topic, on the book that I put you on the link on the previous slide, there is a whole chapter dedicated to that. We can see some example of nonlinearity. All these images have the same, exactly the same contrast, but they are shown using different parts of the image, of the intensity spectrum that you have available. And you can see that you can't distinguish anything in this one. On the beamer, you can see that on the screen on the first one. You can see something here, and you can see a lot in the last one. Actually, probably it's a bit saturated also. Now, we have said that our images are generally 16 bits or even floats. So they cover a large range of intensity. And our screen instead shows only 8 bits of range. How do we display that on screen? There is no single way to do that. You must choose multiple ways. The way that is chosen most of the time is to focus just on one range of intensity. By the way, we are talking about gray images with only that show only intensity, which is one channel. They don't have any intrinsic color, so they are generally shown in grayscale. Not necessarily. We have the next slide will focus on that. So what you show the same brightness on each of the 3 channels of each pixel, red, green, and blue. And what do is you crop the intensity in one specific range. This full image goes from 0 to 1, is a test image that somehow represents something that is shaped somehow like an head, with something that represents the cortical bone. And what you can do, for example, I said, okay, let's plot what happens between 0 and 0.1. We see all of this background here becomes white. You cannot distinguish it anymore from the bone. But you see that you have 2 circles appearing here. And if instead we focus between 0.1 and 0.4, which is 0.1 and 0.3, sorry, you can see that we distinguish a lot very well. These are small details with low contrast. We can see them perfectly. We can see all of these dots here. We don't see anymore the parts that get in the low activity region. And but for example, we lose this superposition here. So it's a trade-off. There is no really straightforward rules. Like if you are working in CT, there are some standard way to crop the intensity range depending on what you want to take a look at. That's the most you can do. However, what we're doing is showing things in grayscale, but our vision, eye plus brain, is able to look also at colors on top of brightness. So what we can do is use a so-called lookup table without realizing that you have done it thousands of times in probably when using PyPlot image show. And these are all options of that also PyPlot image show implemented. What you do is you give x to this function. X is your input image, a lower threshold and higher threshold, and it converts your image in a range from 0 to 1. How? You just crop and rescale. Then what you can do, you can apply a lookup table. You take all this number from 0 to 1, and you map a single number to 3 numbers, one for each between for red, green, and blue. This is the infamous jet scale, which goes from blue to red, which somehow remembers the colors of fire, from a cold object to a hot object. And this is what happens. You have, if you have on a scale from 0 to 255, you take 20, you get the highest intensity of blue. You take 30, you start to add some green and take out some blue, and then you start to add some red. Now, color maps are completely arbitrary. I took this from a PyPlot manual, and this was one of the panels of the color maps that are already implemented. I think that it's something around 100 color maps already implemented by default. Then you can come up with more. These are some examples applied to the previous image. Each one helps you highlight different details. However, you need to take into account the effect of the color map on your perception system. For many decades, the so-called rainbow/jet color map was standard in multiple visualization packages like Matplotlib, in MATLAB, and so on. Now finally, they removed that, but you could see that in 2007, they were publishing papers saying it is still considered harmful. In 2015, they were saying why we shouldn't use that. In 2010 and 2021, they were still discussing why are we using that, why it's not good, why it distorts research. And why is that? Because our brain, we've mentioned that, is super attentive to edges. And edges are perceived when there is a change in color. So this is, let's take these 4 images. They have a linear gradient. These are ramps. And this is a linear change in intensity from the center to the background. So there is no edge anywhere. But if you plot it using the rainbow map, you see almost no variation. You perceive almost no variation when you're in the same color, and then a straight variation, like there was a band, anytime you change color. That's why you need to be super careful when using a color map. Nowadays, the default color map in Python is something that they developed with perception psychologists. I don't remember the exact term, sorry. And they call it's a class of color maps which is called perceptually uniform. So they don't give you the appearance of edges when there are no edges present. This is very important, of course. And okay, no, sorry. Forgetting something, but I don't know what. Okay, then there is another option, which is there is another issue to take into account, which is that of volumes. I've mentioned before that we have that if you have a volumetric image, we have an array which is a 3D array, a stack of planes. How do you visualize that? You can crop it, you can slice it along any of the 3 axes. These 3 axes, by the way, have an anatomical name, which is, you don't need to remember that for now. It's axial, coronal, and sagittal. And in this way, you can use the radiologist, when he's visualizing a CT scan, scrolls through each plane, but some features are best seen in one direction or the other. Now, let's introduce medical images. Medical images can be of really a huge number of types. We can classify that according to the method used to generate the image. We have what's called radiology, which is what the physician with the radiology specialization do. And they have multiple ways to take a look at images, multiple image modalities. They have X-rays, which can be planar or... so this is the physical process that generates the images. It's X-ray. We'll see the properties of these 3 ones, mainly. Magnetic resonance and emission tomography. Then you have ultrasound, which uses sound waves. But in an hospital, you also work with visible photography. When you're doing dermatology, you are taking pictures of the skin. When you're doing endoscopy, like colonoscopy, gastroscopy, and so on, you put a camera, the same camera that is in your cell phone. With endo, we mean entering a natural body cavity, so you can enter into the stomach and so on. We have microscopy, which is still a photography, not necessarily visible. You might, using some fluorescent antibodies, you might look in the infrared, and you don't look at visible, meaning human scale. Maybe you're looking at microscopic scale, but it's still light images. Then you can also work at some signals. That they are not images, but they're still signals. These are things that could have been merged together with medical imaging, because until very recently they were printed on paper and read by human eye, which exploiting the fact that the human brain was very good at picking up patterns. Nowadays we have artificial intelligence that reason in the same way. We can also distinguish images according to the purpose. Why we're doing that? We can take a look at anatomy. Anatomy is the shape of the body. And we can take a look at using X-ray. X-ray look at densities. And generally, different organs or different parts have different densities, so you see the shape of each organ. Magnetic resonance show boundaries. Again, show it's sensitive to chemical composition. When you, I don't know, if you take a look at a joint, you have a ligament, a bone, and the muscle have all different chemical composition. So you see edges with all the regions. So you see if the ligament is integer or it is broken. Ultrasound is sensitive to boundaries because sound waves reflect. Otherwise, you can, there are different modalities that take a look at properties instead of shapes. With emission tomography, you get, you inject a marker in the body, and you see where it accumulates. So you can see which part of organs are activated to be receptive to that marker. Magnetic resonance, I told you that it looks at chemical composition. So sometimes chemical composition can change during a process. So you don't see only shapes, but you can also see properties. And then again, dermatology, microscopy also look at properties after microscopy, especially with proper coloring. We can also distinguish images according to dimensionality. Well, we have 1D. That's not really the case often, but like a signal in time, like an EKG. You can have 2D images, like in 2D, the classical X-ray to see a broken bone. We have tomography, which is a 3D stack of 2D planes. In this case, with tomography, we means generally we refer, I have a slide about that, to a 3D stack of 2D planes, which means that the resolution in one plane is much lower than in the other two axes. Quite often, CT and MR are in this category. We can have fully 3D isotropic imaging, which is a 3D matrix of pixel or voxel. And they can, if they are isotropic, they can be sliced really in any dimension. And then it's also possible for display purposes, which can actually be very useful maybe in surgery, 3D renderings. Like you take a CT scan of a leg, you give it to the orthopedician, he displays a 3D rendering and he understands the shape of the bone. Let me give you an example of tomography. This is a 3D MR of the brain. already the pixel sizes are 0.8 millimeters times 0.8 millimeters times 5 millimeters. You can see that the resolution, this is what I meant by the resolution along one axis is much worse than along the other two. It takes time to acquire each plane, so if that is sufficient for your task, you will you don't need to acquire more data. Data are quite costly to acquire here. Of course, it's nicer to see fully 3D resolution along all axes, but that's not always the case. Let me summarize in yet another way the properties of these images. Here we have a plot with, in two axes, the spatial resolution that we can achieve, and on the other axis, the sensitivity to the concentration, the chemical concentration of what? Of our targets of interest. And in this case, we have X-rays. X-rays are not really sensitive. They just take a look at the density. They can get quite high resolution in preclinical. Preclinical generally means mice and rats, or ex vivo specimens, which means samples that you have extracted, like a piece of a bone or things like that. But that's not in vivo anymore. This course will focus mostly on in vivo techniques. You can go down to 20 microns of spatial resolution. But it's not really sensitive to concentration of anything. MR has a pretty high spatial resolution. In vivo in human, you can go to lower than 1 millimeter, half a millimeter or so. With preclinical, again, mice, MR, you can go to 100 microns or less. And according to the imaging modality, you can be sensitive to the presence of certain chemicals. When you are working with spectroscopy, you can really identify very small concentration of some random molecules, but at higher resolution and very low spatial resolution. With nuclear medicine, we have a very poor spatial resolution. We have like 1 centimeter, or if you are lucky, half a centimeter of spatial resolution, which means 80 pixels across the abdomen of the major axis of an abdomen of an adult. It's not really not that much. But you can even go see the presence of receptors to specific drugs in the brain with a concentration of 10 to the minus 12 molecules, which is amazing. With mice, you can go to much higher spatial resolution. And in microscopy, with antibodies or so, you can go really to extreme spatial resolution and extreme chemical sensitivity. But of course, microscopy is, you need to do an operation, extract a sample, send it to the lab, 1 week or 2, and then you know the result. This is real time. There are even some nuclear medicine techniques that can be used during an operation. We can also discuss about the use of ionizing radiation. Ionizing, to the non-specialist, we can say the bad kind of radiation. X-ray and emission tomography use ionizing radiation. MR, ultrasound, optical imaging do not use ionizing radiation. MR has no known health risks, which is, okay, there might be unknown, but given that it's been used massively for 20 years, we can say that if there is something, it's really residual in terms of risks, but it's, I mean, there are some known effects if the device is not calibrated, but that's a separate issue. With X-ray, we know that there will be some damages. Now, let me close these. That's really not really the closure. Let me talk 5–10 minutes about radiation safety. Some elements. This is not something that I will ask you in the exam, but I guess that is a very important general knowledge. And this often is the answer to many questions about this. Why don't we do this exam instead of that one? Why don't we acquire much higher spatial resolution? Why don't we do a follow-up every week? More often than not, the answer is radiation safety. The mechanism by which radiation do harm in the body is not really some nuclear interaction of weird stuff. It's ionization in water, of water. It creates some free radicals which diffuse, and then they react with the DNA, and it breaks the DNA chain of the cell. Actually, like most other kinds of dangerous substances or venoms or poisons or things like that. In 30% of the cases, the ionization happens directly in the DNA, and the DNA chain is broken. If a chain, so in both cases, the DNA is broken. If in one cell you have a DNA broken once, in most cases it's repaired, and it's not an issue. If it's broken in 2 points, it's unfixable, and the cell dies. So there is really nothing special about radiation as compared to most chemical substances. The dose is measured using this unit of measure, which is called a sievert. Like any chemical substance you can be exposed to, the radiation can give you 2 kinds of effect. Deterministic and stochastics. The deterministic ones will happen definitely, and they will happen immediately, let's say. They also happen after a threshold and in a dose-dependent manner. With increasing, they start from 500 millisieverts, from half a sievert. You start to have skin burns, hair loss, infertility, cataract, and then you can go, you can have malformation of the fetus for pregnant women. And if you go higher than 2 sieverts, you can have acute radiation syndrome, which if untreated, or if the dose has been much higher than 2, around 3 or so, will lead in 2 to 3 weeks to death. On the complete opposite of the spectrum, we have stochastic effects, which happen when you get an exposure of around 50 millisieverts per year. So we talk about 1/10 or 100 of when you start to have each on the screen, so a completely different range. It's stochastic. Why? Because it modifies the probability of something happening in every future year of the remaining life, let's say. The effect depends on the radiation sensibility of each cell population. Therefore, due to how cell works, the younger population is much more sensitive. There is no known thresholds, no known safe threshold, and the possible outcome for that is cancer, which of course is pretty different. This is, if you take this high dose, next week you will have this effect, or tomorrow you will have a skin burn. This is maybe in the next 60 years you will develop something. This is also much, much harder to quantify. Now, the average dose in the United States of America is 6.2 millisieverts per year. On the average person of the United States, the medical exposure nowadays is up to 50% of the radiation dose that one is exposed to each year. So it's quite of a concern. Of course, there is extreme variability between subjects. Here we have some how this is broken broken from the various sources. The radiation, the terrestrial background is around 0.2 millisievert. This is radon and thoron in rocks around us. Then there is internal sources. It's the radiation that we have within our body, mostly potassium, and you cannot live without potassium, so don't skip that. Then there is the space radiation. This is all the cosmic rays, is another 1/3 of a millisievert. I don't see travel, because plane travel has quite a lot of radiation dose due to the cosmic rays, because when you go to high altitude, you get many more cosmic rays. And then you have computer tomography, nuclear medicine, and interventional fluoroscopy. Now, maybe terrestrial is the one with cosmic ray. Radon and thoron is 2.2 millisievert. Actually, this is, it has a lot of variability, because according to where you live, it can go from like 0.5 or things like that. But if you go in some places like with a lot of turf, tufo, there you get lots and lots of radon in the air of your home, and then you can go to up to 20, 50, so you get a factor of 20 between just due to the village where you live. And of course, the medical dose depends a lot on how many exams you need to take. Many people can go for decades without a single examination, while some sadly need to do many exams. Now, let's take a look at the dose that you typically get in one medical examination. You can see that it spans a huge range of possibilities. So you need to really, when you say there is radiation in this exam, it's not really meaningful, because if you need to take the X-ray of your hand for a suspect broken bone, you get 0.005 millisieverts. If you do the dental bite wings that your dentist might take once a year, you get 0.04. The chest projection that's often used in the hospitals for whichever reason, for the most disparate reason actually, not really for whatever, because it's super useful. That was what I meant. It's only 0.1 as compared to 3 millisieverts a year from just for the environment. On the other side, if you go to a fluorine 18 PET, you get 7 millisieverts. So if you do a contrast CT of the chest and the thorax, that is really a lot of those. It goes to 20 millisievert. That's really something you need to think carefully about. This also has a bit of variability, because it depends on lots of factors and the age of the machine, the standards of your nation. And luckily enough, is coming down with years. So the takeaway message is most X-ray based imaging procedures have completely negligible doses, so you don't need to worry. However, some specific radiation procedures, especially if repeated and in young age, can be quite harmful. However, like if you are 20 years old and you get a lymphoma and you need to do a follow-up, that's better than not doing the follow-up. If they ask you to do 1 CT a year, let's have it. The cost benefit, you get higher chance of cancer in the next 30 years, but that's better than the other option. Of course, people that focus on radiation safety of examination should work to reduce the number of exams and the dose of each exam. Okay, so the last 2 or 3 slides. What are the file formats that are usually used in medicine? The most used one is the DICOM, which is an abbreviation of the Digital Image and Communications in Medicines. It was invented in the 80s, and it was a standard for all kinds of medical images. It has a large set of headers, possibly infinite, because you can see on the collaboration website a dictionary with hundreds of pages for all the possible modalities. Plus, there is the possibility to have private headers that, I don't know, one manufacturer can add to the modality. So this has been invented to be manufacturer independent, modality independent, and so on. It can encapsulate images of different formats. So you can have also like a screenshot embedded in a DICOM file. Sometimes there is the need for that. It's interesting. I mean, it's super useful because it is able to handle network communication within an hospital and between hospitals in the same network. So there are DICOM networks within hospitals. When the radiologist does the reading, that's the technical term, he's generally in another room compared to the acquisition room, and it goes into the internal database, which is a DICOM database, and it says, okay, download the exam for this patient. It downloads it, and there is also a standard which, in the end, is quite efficient. It allows reading images for very old previous examination. Now, the issue is that it's very bulky, and it has a gigantic overhead, and many headers can be non-standard, sadly. The other option is the nifty file format. This is a format used exclusively for neuroimaging. And it has only 348 bytes of header with very few fixed fields. This can be used only for research. The first one instead is used for clinical reading. There are lots of servers and clients that are FDA certified. It's the most standard thing ever nowadays. And this includes only orientation information, not even patient name. Can store volumes up to 5 dimensions for the reason that we mentioned. It's used only for research, for neuroscience research specifically, but massively in this field. Okay, last thing, there is here a useful resource. Actually, I haven't checked it if it changed in the last year. Is the website radiopedia.org. It's designed for physicians, and it's extremely popular with them. It has some multiple brief description of pathologies, so if you have curiosities, you can go and look it up. It has very short summary of useful information of most radiology imaging techniques. It has lots of examples of images of both of modalities and of pathologies. However, it's a for-profit website, so it might have a bit of annoying ads. Okay, so that's it for the theory.